All right. So welcome to NatSci 6103 for Chemistry for Engineers. For this week one, for the first week, so these are the main topics that we are about to tackle. So we have the introduction, matter and its properties, atoms, molecules, and ions. Okay. So for this module, this will be our learning outcomes. So by the end of this module, you should be able to understand and 1, define the meaning of chemistry. 2, explain the properties of matter and ways of classifying matter. 3, differentiate elements, compounds, and mixtures. 4, determine SI units in calculations and significant figures. 5, differentiate between precision and accuracy. 6, summarize Dalton's atom theory. 7, describe the atomic structure, electrical charge, and relative masses of protons, neutrons, and electrons. 8, identify atomic number, mass number, and isotopes. 9, explain how elements are arranged in the periodic table. 10, differentiate empirical formula and molecular formula. 11, write empirical formulas of ionic compounds, name molecular compounds, and acids. Okay. So these are the topics that we are supposed to go over in this module. So let's start with the study of chemistry. Okay. So by definition, chemistry is a branch of physical science that studies matter and its properties and behavior. Okay. So anything that has mass and occupies space is referred to as matter. So the very classic definition of matter. Right. So again, chemistry studies matter, and matter is anything that has mass and occupies space. Elements are the basic unit of matter and cannot be broken down into simpler substances by ordinary chemical processes. Right. So the list and characteristics of the elements are can be found in the periodic table. Infinitesimally small building blocks of matter are referred to as atoms, okay? And molecules are substances with 2 or more atoms joined together. Okay, so we have a figure here. So one atom, one of this round thing is an atom. Okay, if there is more than one atom in a we call that molecule. In the first or in the 2 upper illustration, we have here 2 hydrogen atom and 2 oxygen atom. Although these are elements because these are atoms, or rather, these molecules are made up of the same element. But in hydrogen and oxygen are naturally found in this structure. They are naturally found as molecules, right? And then we have H2O as water, hydrogen peroxide, H2O2, and so on and so forth. So these are some examples of our molecular models, right? So before we jump to the big guns, to our atoms, molecular compounds, and whatnots. So let's brush over some of the most basic principles in our physical science or chemistry. So the unit of measurement, right? Properties of matter are mostly calculated by numbers or quantitative. Units of a quantity must be specified when a number represents a quantity that is measured. Okay? So again, let's go back to that second sentence. Units of a quantity must be specified when a number represents a quantity that is measured. Okay. What does this mean? This sentence actually seem very complicated, right? Okay. Units of a quantity must be specified when a number represents a quantity that is measured. What this one is actually just trying to say that when you are stating a quantity, state what that quantity is all about. Let's say, for example, you say you have 100. 100 what? Right? So 100 pesos, 100 kilograms, 100 stones, right? So whenever you mention a quantity, you should always specify what kind of quantity is, or what type of quantity is being measured. That type of quantity being measured is what we call the units, right? We have two types of units. We have metric and we have English units. Sorry. We have two, the two of the most popular unit system of measurement is metric system and English system. Here in the Philippines, we are mostly using metric system, but not 100%. Right? The whole world in majority is using metric system, but of course there's still a large number of countries that are using English system. Okay. If you think about it, since we have different types of measurement system, right? It should be a hassle to convert every now and then. So actually, we have what we call the SI units, right? So in 1960, the International System of Units was agreed as the preferred units in scientific measurements. So this is what we call the SI units. So in terms of scientific measurements, these are the standards. Whenever you are making scientific measurements, you should follow or you should use SI units. So these are the 7 SI-based units. We have for mass, kilograms; for length, meter; for time, second; for temperature, Kelvin; amount of substance, mole; electric current, ampere; luminous intensity, candela. Okay, so these are the 7 SI-based units. Okay, question. Since SI units was found, why is it that there the countries that are using anyway SI units are patterned from metric system, right? So since in other words, metric system has been like the standard, but why is it that the English unit using countries have still not converted to metric system? I think one of the most popular countries that is still using English unit is the United States of America. Okay, so most of the people there are still using English units. They're using miles for distance, Fahrenheit for temperature, and so on and so forth, pounds for weight, and so on and so forth. Right? Why don't they comply to the international standards? Okay. So this is actually one of the reasons. The SI unit was founded in 1960. So before 1960, English unit using the countries that are using English units has all of their documents in English units, like learning materials, scientific journals, newspapers, technical drawings, building drawing, water system drawing, so almost some of their machines are patterned to use English units, right? So if they were to follow the international standard units or the SI units, they will have to recall all of those instructional materials, all of those books, all of those scientific journals, all of those newspapers that have been publishing that have been using English units, all of those technical papers, like technical drawings, like building plans, have to be redrawn to accommodate the metric system. All of the machines that have been calibrated to English units should be recalibrated to metric units, right? So in order for them to convert to international standard or to metric system, they will have to spend a lot of time and a lot of resources. So in the long run, it is not worth it, right? So they stuck to their English units. Right? So that's why we have English and metric system still existing, coexisting. So anyway, it is not much of a hassle, by the way. So when you come from the Philippines, you go to US, use there. You just convert whatever you're using to the unit that they are using. Okay. So that's the story of the English units. Anyway, so let's proceed. So we will try to go over these base units for the next discussion. So we have mass and weight. So mass is the measure of amount of matter in an object. Okay. But weight is the force that gravity exerts on an object. So weighing is the process of measuring mass. Okay. So I'm sure some of you have been asking this question. So every time you have like a physics class or chemistry class or whatever, why is it that in our country we call it weight when we are referring to the mass? We call it weight, but the unit is kilograms. Excellent. Okay, we call it weight, but we're actually referring to the mass, and so on and so forth. Okay. Let's have this example. I'm gonna draw. Please bear with my drawing. Let's draw a. Imagine a weighing scale. Then this one. By the way, if you're curious, I'm using xvaluedraw.com. Something good because I'm not that good in drawing. Anyway, so let's have this. Imagine a weighing scale. Just imagine. This looks nothing like a weighing scale. Okay. So what is the story between mass and weight? For example, you are buying 1 kilogram of chicken. So that 1 kilogram of chicken will be placed in this weighing scale. Okay. But is it the mass that is activating the weighing scale? No, it is the weight. So what is the difference between the mass and the weight? So the mass is 1 kilogram. The weight is actually equal to mass times acceleration due to gravity, but it is so using G for gravity. Okay. So if you can still remember, our unit for, or rather the value for G or acceleration due to gravity is equal to 9.8 meters per second squared. Okay. So multiplying, we will have 9.8 kilogram times meter per second squared. And kilogram times meter per second squared is equal to newtons. It's also known as newtons. Okay. So mass, weight. But when we place our 1 kilogram chicken on the weighing scale, it is actually the weight that pushes the weighing scale and turns the dial. Okay? This is an analog weighing scale, by the way. Most of the weighing scale nowadays are digital. Okay? So, although it is the weight that has been activating the weighing scale, this dial was calibrated such that when the weighing scale experiences 9.8 newtons of force, it will turn in this direction. They labeled that direction as 1 kilogram because only a 1 kilogram mass can apply 9.8 newtons of force. Okay, so that's the story between mass and the weighing scale. But since common people has been referring to this 1 kilogram as weight. But anyway, that is not much of a big deal since although people has been saying it wrong, but well, there's no war that caused that misconception. I think all is good. I think it's weirder if we're actually gonna use newtons to refer to weight. Like, imagine buying 30 newtons of tilapia in the market. Okay, so let's just stick to kilograms. Anyway, I just want to clarify what happened with the mass and weight in the common setting. Anyway, the SI unit of mass is kilograms. Okay, so 1 kilogram is equal to 1,000 grams or equal to 1 times 10 raised to 3 grams. Okay, hopefully there's a little bit of a memory in there regarding our prefixes for scientific notation. Okay, so some of the most popular is kilo, which is 1,000, mega, which is 1 million, giga, which is 1 trillion. Okay, and then centimeter, which is 0.01, decimeter 0.1, millimeter 0.001, micrometer 0.000001, and so on and so forth. So those are the prefixes for our scientific notation. So I hope you still remember those. Okay. So that's it for our mass and weight. Next, volume. Okay. So meter is defined as the SI unit of length. So the SI derived unit for volume is the cubic meter. So why did we say that the SI derived unit for volume is cubic meter? Let's take the rectangle, for example. Okay. So the sides of a rectangle is length and width. They are both lengths, but we just call them length and width. So length is in meters, width is in meters. So for the area, that would be meters times meters. So square meters, right? So the unit of area is square meters. In the case of volume, okay, when we have, let's say, rectangular parallelogram. Rectangular parallelogram. The formula for a rectangular parallelogram is, or rather the formula for volume of a rectangular parallelogram is length times width times height. Okay, it's a little bit of geometry in here. So length times width times height. Length is in meters, width is in meters, height is in meters. So meter times meter times meter, meter is to 3 or cubic meters. Thus, the SI derived unit for volume is cubic meters. Okay, just want to emphasize that part. The more common unit of volume is liters, right? This is what we usually encounter in our daily activities. Our soft drinks is in liters or ml. Water is in liters or ml. Most of our liquid necessities like oil, whatever, petroleum, it's in liters. What else? Right. Most of our liquid necessities are expressed in liters their volume is expressed in liters. Okay, so 1 liter of volume is equal to 1,000 milliliters or 1,000 cubic centimeters. By the way, cubic centimeters is also popularly known as cc. But I'm sure you've heard of that, right? So cc. In medical setting, usually liquids used in medical setting are expressed in cc. And then, so 1 liter is equal to 1,000 milliliters or 1,000 cubic centimeters or 1 cubic decimeter. Okay, so that's for the unit of volume, which is liter. Next, density. Okay, so density is defined as mass over volume. So when an object is more dense, meaning it is more compact, in a small volume, it can contain a large number of mass. So between liquid, solid, and gas, so the more dense is solid, of course, and the least dense is gas. Okay, so to help you understand why, let's take, for example, a 1 liter plastic bottle. Okay, 3 1 liter plastic bottles. So one of them will be empty, one of them will be filled with water, and then one of them will be filled with sand, right? So they are the same volume, which is 1 liter. In terms of mass, this sand is actually heavier compared to water, meaning there is more mass in the water bottle that contains sand as compared to the water bottle that contains water, as compared to the empty water bottle. By the way, the empty water bottle is not really empty. It contains gas, okay, or air. It contains our atmospheric air. So that is proof that solid is more dense, is the most dense as to the three. Okay, so where did we stop? So there. So we have just proved that solid is the most dense as compared to liquid and gases. And the gas is the least dense among the three. Okay, so kilogram per cubic meter is identified as the SI derived unit for density since mass, or since the SI unit for mass is kilograms and the SI unit for volume is cubic meters. However, for solids and liquids, more commonly used are grams per cubic centimeter and grams per milliliter. Okay? So due to low densities of gases, these are expressed in grams per liter. So anyway, let's proceed. So I hope density has been clear to you. Next, we have temperature scales. So temperature scales. Temperature is defined as the measurement of the degree of hotness or coldness of an object. Okay, so there are 3 temperature scales that are being used. 3 most popular temperature scales that are being used: degrees Celsius, degrees Fahrenheit, and Kelvin. Okay, degrees Celsius is for metric units, degrees Fahrenheit is for English units, and then Kelvin is the SI base unit of temperature, or also known as the absolute temperature scale. Notice that there is no word degrees for Kelvin since that is absolute. Okay? It has no negative value since the lowest possible temperature is 0 Kelvin. Okay. For degrees Celsius, the freezing point of water is 0 and the boiling point is 100, as we all know. For Fahrenheit, that is 32 degrees Fahrenheit freezing point and 212 degrees Fahrenheit boiling point. Okay. Then we have this conversion from Fahrenheit to degrees Celsius. Okay, so even though you can just like type in Google 36 degree Fahrenheit to Celsius and it will show up. But let's still try to understand how the conversion works. First formula will be conversion of Fahrenheit to degree Celsius. Second formula is conversion of degree Celsius to degree Fahrenheit. And then the last formula is the conversion of degree Celsius to Kelvin. Okay. Let's have the first formula. So degree Celsius to degree Fahrenheit. For us to have a reference that is already established, let's use the freezing point and boiling point to check, to confirm these formulas. Right? Let's use the boiling point. Right? So the boiling point of water in degrees Celsius is 100 and in Fahrenheit is 212. So 212 degrees Fahrenheit boiling point is equal to 100 degrees Celsius boiling point. So let's try to prove that this conversion is actually correct. So let's use our formula to convert Fahrenheit to degrees Celsius. Okay, let's use the first formula. So degrees Celsius is equal to the value in degree Fahrenheit minus 32 times 5 over 9. Okay. So we are converting 212 degrees Fahrenheit. 212 minus 32. By the way, if you're wondering what am I using, I'm using this website, excalibur.com. 5 over 9. So 212 minus 32, that is 180. Okay, times 5 over 9. So 180 divided by 9 is 20. 20 times 5, that is 100. Okay, so we have just confirmed that 212 degrees Fahrenheit is actually equal to 100 degrees Celsius. Okay. Next, let's confirm our second formula. So we've used the boiling point, so I think we should use the freezing point. So the freezing point in Celsius is 0, in Fahrenheit is 32. Okay. So 32 degrees Fahrenheit is equal to 0 degree Celsius. Okay, so this time we will convert Celsius to Fahrenheit in the second formula. So degree Fahrenheit is equal to 9 over 5 times degree Celsius, which is 0. Plus 32. Okay, then 9 over 5 times 0 plus 32. Then this will be 0. So degree Fahrenheit is 32. Okay, so we just confirmed the conversion of the freezing point and boiling point of water from degrees Celsius to degrees Fahrenheit. Okay, so I know it's too much to memorize the formulas, but to help you try to remember this formula, okay, we should not Anyway, this applies to all formulas. Right? You should not memorize the formula, but you should understand how the formula works. Okay? What do I mean by that? If you notice, okay, whenever we convert degrees Celsius to Fahrenheit, the quantitative value is actually increasing, right? Right? And then when we convert from Fahrenheit to degrees Celsius, the quantitative value is decreasing, right? So in this formula, there are only three. There is three numbers that you should take note of. We have 32, 5, and 9. Okay. So when converting from degrees Celsius to Fahrenheit, the value should be higher. So meaning we should add 32. And when we multiply, it should be 9/5 to increase the value. And when we are converting from Fahrenheit to degrees Celsius, meaning the value should decrease. So what we will do with 32 is we will subtract, and then what we will multiply is 5/9 to lessen the value. Okay, so that's it. That's just a tip anyway. It's not a foolproof. But yeah, that's it. Anyway, let's proceed. Then the last one, we have Kelvin. So Kelvin is simply degrees Celsius plus 273.15 degrees Celsius. So whatever the value in Celsius, you just add 273.15. That's Kelvin, right? There's actually another temperature scale, but it is not as popular and not as used as the other three. Right? So we have okay. So what does this Rankine do? Notice that Kelvin and Celsius are what do you call this? Are associated. No. Kelvin corresponds to degrees Celsius. Okay, so Rankine is actually a temperature scale that corresponds to degree Fahrenheit. So this is also an absolute temperature scale, but it corresponds to degree Fahrenheit. So I'm not sure of the value. I think it's 459.67. Please take the green. So there's a chance that it's wrong, but double check. Yeah, 459.67. So that is for that conversion to Rankine. But again, it is not as useful and as it is not as commonly used and as popular as the other three. So it's not included in the original slide. I just introduced it to you just in case you encounter Rankine in the future. Okay, so that's it. That's for our temperature scales. Okay, so let's proceed. Clear the doodles in 5, 4, 3, 2, 1. Next. Accuracy and precision. So this is a very classic topic ever since high school. Okay. So accuracy refers to a measure of how close the individual measurements are to the actual or true value, while precision refers to as to how closely individual measurements are to each other. In other words, accuracy is the correctness. Okay? How correct? That is accuracy. Precision refers to consistency. Okay? If the values are consistent or are close to each other. So to help us understand more, we have some visual representation here. So the classic dart and dartboard visual representation for accuracy and precision. So for first visual, so we have 3 darts very far from the target and very far from each other. So this is an example of a low accuracy and low precision measurement. On the second visual, the three darts are very far from the target, but they're hitting the same area in the dartboard. So the accuracy is low since they are far from the target, but the precision is high since they are close to each other. The third visual, we have the three darts close to the target but are far from each other. This is an example of a high accuracy and low precision. Okay, and then the thirdly, the darts are hitting the target, high accuracy, and they all hit the target. So they are near each other, so high precision. Okay, so notice that you usually hear the word precision in machines because in the case of machines and even programs, precision is very important because it shows that the machine or the system is stable because it is always hitting the same value every time. If it is hitting random values, then the machine or the system is not precise, meaning it is not as reliable compared to a precise system. Okay, so anyway, that's it for accuracy and precision. So next topic, we have significant figures in calculations. Okay, so what about significant figures? This has always been a huge topic in any sciences, physics, or anything. So definition. Significant figures are the digits in a measured or calculated quantity. For example, a measured value of 3 kilograms has 2 significant values, while a value of 3.3 kilograms has 3 significant values. Okay. In defining significant figures, read the numbers from left to right with the start of count from the first non-zero digit. Before we proceed to the rules of counting significant figures, we need to understand first why significant figures is important. Okay. For example, you have 1,500,000 pesos. Sorry. Excuse me. In your pocket right now. So 1,500,000 pesos. Okay. So if we will take the significant figure or significant value, significant figures of this amount, okay. So the non-zero digits here are 1 and 5. So these are the significant figures. 1,500,000. Okay, so what does this mean? This is an estimate. But for example, the actual amount that you have is 1,500. 1,500, let's say 35,100. Okay. What does this two significant figure means? It means that what is only important to you right now is the 1 million and then the 500,000. Whatever amount is found in here is not really significant. This 35,798 is very small compared to the 1,500,000. So would you care about the 35,798 if you have this much money? So I don't think so. I think this will look like change to you. So they become insignificant. Okay. So the premise of significant numbers is you're identifying the place values or the decimal place, sorry, the place values that are important in your measurements. Okay, and then the rest of those numbers, whatever their values may be, is not significant anymore because usually in measurements or in scientific studies, they affect the effect that they have on the system is 0 to very minimal. Okay? You only care about the values that will have major effect to the system. Okay, so now that we are clear and as to why significant figures is important. Okay, so let's go with the rules. So rule number 1 in defining significant figures, read the numbers from left to right. So always from left to right. Read the start of count from the first non-zero digit. So for our example, this 1,500,000. So we started from the left. The first non-zero digit is 1, then 5. So the rest will be not significant because 1 and 5 is the only significant numbers here. Okay. How about the zeros? Are they always not significant? No. There will be times that there are cases that the zeros are significant. Okay, so these are the rules. Zeros are always significant if located between non-zero digits. Okay, for examples, 209 grams. Okay, so counting from the left, okay, first non-zero digit is 2. 9 is non-zero, so this is significant. Okay, this 0 is between 2 and 9, which are both significant. So by this rule, zeros in between non-zero digits will always be significant. So 209, 3 significant figures. Okay. Next example we have is 4.017. So again, counting from the left, first non-zero digit is 4, then 1, 7. So this 0 here is between 2 non-zero digits. So this will be also significant. So we have 4 significant figures. Okay. So I hope this is clear. So let's proceed to our other rules. I will clear the doodle in 5, 4, 3, 2, 1. Second rule, zeros are always not significant if located at the beginning of a number. Again, the rule is to count from left to right. So, and then the left to right, and then the first non-zero digit. The left to right, the first non-zero digit is 5. So all of the zeros that will pass by is not significant since this is the first non-zero digit. Okay? Not significant, beginning. Next example. First non-zero digit is 7. Right? Significant, significant. So all of the zeros before that are not significant. So 2. Okay? Right. So let's proceed to the next rule. Zeros located at the end of a number are significant if the number has a decimal point. Again, zeros located at the end of a number are significant if the number has a decimal point. Left to right. First non-digit is 4. Significant. Okay? Zeros located at the end are significant. The rule before that, beginning, zeros at beginning, not significant. Zeros at the end are significant. So 4, 0, 0, and has a decimal point. This is the most important part. Has a decimal point. Okay. Next example is 6.0. 0 at the end, decimal point, significant. Okay, so those are the rules for the zeros in our significant figures. So next, let's Let's go to the next rule. I'll clear the doodles. 5, 4, 3, 2, 1. When numbers end in zeros without decimal point, zeros are usually considered as not significant. So in this case, exponential notation is used to identify the zeros that are not significant. For example, 20,200 grams. Okay. So let's have a little refresher regarding our scientific notation. 20,500. 20,500. The number one rule in scientific notation or in doing scientific notation is to locate the decimal point. So if we have a whole number, the decimal point by default is at the end, right? Okay, so this is the decimal point. Then the form or the appearance of a scientific notation is always a single digit times the 10 raised to a certain number. So single digit. So if we are moving our decimal point to the left, so we will stop at the last non-zero digit. Okay. In this case, we will be moving our decimal point 2, 3, 4. We will stop at the last non-zero digit. In this case, it is 2. So this time it will be 2. 2.05. Okay. But is 2.05 right? No, because this is 20,500, so it will not be equal. So what we will do is we will multiply it by a certain number. So what is that certain number? Right? Remember that these place values are actually represented by this. This is the ones. This is the tens, right? This is the hundreds. This is the thousands, 10,000s, 100,000s, 1 million, millions, and so on. Can you see the pattern? Okay. So every time we move away from our decimal point, we are actually multiplying by 10. Okay, so 10, 10, 10, and 10. So 10, 10, 10, 10. We multiplied 10 4 times. 10 raised to 4. Okay, times. That's 2.05 times 10 raised to 4. Okay, so I hope you were refreshed by this review of our scientific notation. So let's have another example. Let's do a right side example. So 0.0000679. Okay, so same, although there is a little difference when we are moving to the right, we will stop at the first non-zero digit. When we are moving to the left, at the last non-zero digit. To the right, at the first 1, 2, 3, 4, 5, 6. Okay, so this will become 6.79. Okay, so same format times 10 raised to how many times we move. So we have 1, 2, 3, 4, 5, 6, 10 raised to 6. But there's a catch. Okay, when we are moving to the right, we are actually going to a smaller number. Why? This one is the tenths, 0.1, hundreds, 0.01, thousands, 0.001, 0.0001, and so on. Right? When we are moving to the left, we are multiplying by 10. But when we are moving to the right, we are dividing by 10. Okay, so since it is a divide, law of exponents, multiplication is plus or adding of exponents. Division is subtracting exponents. So this will be negative, right? So that's it. That's it for our scientific notation. So I hope you were refreshed by this review of our scientific notation. Anyway, let's go back to the significant figures because this is actually our topic. Significant figures of scientific notation. Okay, so after expressing the number into scientific notation, the base 10 is now irrelevant in terms of significant figures. They are not significant. Okay, what matters is the number. So in this case, we have 2.05, 0 in between. So 3 significant figures. Okay, 2.050. 0 at the end, the number decimal, so significant. So we have 4, 2.05000, in between, at the end, decimal, so 5. Right, so that's it for our scientific notation. Okay, so I hope questions. Right. In performing addition and subtraction and multiplication and division, there are additional rules and significant figures in calculations. Okay, I will remove the doodle. Whenever we are adding and subtracting numbers and we want to observe the proper allocation of significant figures, so these are the rules. The result should have the same number of decimal place as the value with the least number of decimal places. Okay, so let's look at the values. We have 10.15, 3.221, and 65.3. So let's look for the value with the least number. 2 decimal, 3 decimal places, 1 decimal place. So the result should have 1 decimal place since it is the least one. So adding these 3 values, we have 78.671. But since we have to follow this rule, the value with the least number of decimal places, so it should be 1. So we will round it off to 1 decimal place. So we get 78.7. So the final answer to be reported is 78.7 because 65.3 has only 1 decimal place. All right. Questions? No questions. Okay, so let's proceed. I will clear the doodles now. 5, 4, 3, 2, 1. Next is for multiplication and division. So in the case of multiplication and division, the result should have the same number of significant figures as the value with the least number of significant figures. Right? In addition and subtraction, we follow the least number of decimal places. In multiplication and division, the least number of significant figures. So we have here an area, a solution for an area. So area is equals to 5.4423 centimeters times 3.5 centimeters. So more or less, this is a rectangle. Straightforward solution, length times width. Okay. So one of the values is 5.4423. So the significant numbers is 5. The other value is 3.5. The significant figure is 2. Okay. So multiplying, we get 19.04805. But since we are to follow the rule in significant figures, we follow the least number. We have 2 significant figures, so we have to round this off. We get 19 square centimeters. Okay. So that's it for our significant figures. Question: is significant figures always being followed? Supposedly, but in the school setting, since we are not dealing with a very accurate answers, so usually in our problems it is stated how many places the answer should be or how many decimal places the answer should be. But if it's not, usually the default one is 2 decimal places or 3 decimal places. Anyway, so I hope we're good with this. I will clear the doodles. 5, 4, 3, 2, 1. So next. So now we move on to matter and its properties. Okay. So one, we have the classifications of matter. Classifications of matter, we have physical state, which is solid, liquid, or gas, and composition, which is element, compound, or mixture. Okay. So the states of matter, so the classic, solid, liquid, and gas. So right now we have many other states of matter, but in everyday activity, the ones that we are only experiencing or we can only interact with is solid, liquid, and gas. The other states of matter is a very special case ones. Like for example, the plasma. Plasma is air subjected to a very high temperature. Okay, so we don't see that every day. And then Bose-Einstein condensate, that is also a phase of state of matter. That is the condensation at 0 kelvins, or the absolute 0. We don't experience absolute 0 every day. Okay, so we just we just stick to solid, liquid, and gas. So the very classic definition: solid, fixed shape, fixed volume; liquid, no shape, no fixed shape, definite volume. Wait. Let's change the definition. Solid, definite shape, definite volume. Liquid, no definite shape, definite volume. Gas, no definite shape, no definite volume. Okay. So we have here a visual presentation. So solid, again, definite shape, definite volume. Liquid, definite volume, not definite shape. Gas, not definite shape, not definite volume. Okay, so states of matter can be converted from one state to another by having changes in temperature and or pressure. So the most common ones that we know, of course, so from liquid to solid, wait. From solid to liquid, we have melting. From liquid to gas, we have evaporation. Gas to liquid, we have condensation. And then liquid to solid, we have solidification. Okay. And then we also have solid to gas sublimation. Example is the naphthalene balls or the mothballs. Then from gas to solid or deposition. So that is the six changes in the state of conversion of the states of matter. Okay, so I hope you're good with that. This is a review. Properties of matter. So matter is identified by either its physical property or chemical property. So physical property can be measured and observed without changing the identity and composition of a substance, such as color, smell, hardness, density, melting point, and boiling point. Chemical property identifies the way a substance changes or reacts to form other substance. So flammability, or the ability to burn a substance in the presence of oxygen, is one example of a chemical property. So we move along, we will discuss this more in the next slides. Okay. So measurable properties or physical properties are further classified into the following. So we have intensive property and then extensive property. So intensive does not depend on the amount of matter being observed. Examples: temperature and density. A good example would be water. Okay, the boiling point of water is intensive because 1 liter of water will boil at 100 degrees Celsius, and 1 drop of water will boil also at 100 degrees Celsius. So the amount of water, the amount of matter of the water does not, rather that the boiling point does not depend on the amount of matter of the water. Tongue twister. Anyway, extensive property.